Hi, this is going to be a quick video over mass percent, empirical formulas, and chemical formulas. To find mass percent, you're just going to take the total mass of your element in your compound and divide that by the mass of the compound and then multiply that by 100. And when I say mass, I'm talking about the weight from the periodic table. So for example, I have 2 hydrogens in water, and each hydrogen has a mass of 1.008. So that means I have a total of 2.016 grams of hydrogen in my water molecule. And what is the mass of water? It's 18.016. Okay, so this is just like what we've been doing with stoichiometry, where you add up the weight from the periodic table. That's where I get the 18. 16 for oxygen plus 1.008 for each hydrogen. And because we have 2 hydrogens, that's why this is 2.016. Okay, in the last step, just multiply by 100 to make it a percent. And this gives us a mass percent of 11.19% hydrogen in water. Okay, the second one, we're going to look at the mass percent of oxygen in water. And oxygen has a mass of 15.9994, so I can go ahead and round this to 16.00, or you can just write it as 16. There's only 1 oxygen, so we only have 16. And then the total mass of water is 18.016. And we're going to multiply this by 100 to give us a percent. And that's going to give us 88.81% oxygen in water. Okay, notice that our percents add up to equal 100%, which makes sense. These are the only 2 elements in water, so their percents should add up to a total of 100%. Okay, so that's our first example. Now let's look at a couple others that are a little bit more complicated. So here we're looking for the mass percent of nitrogen in ammonium sulfate. And in ammonium sulfate, I have 2 of these NH4s. That means 2 ammoniums. That means that I have 2 nitrogens. And each nitrogen has a mass of 14.01, and so that means I have a total of 28.02 grams of nitrogen in my compound. Okay, then I just need to add up the weight from the periodic table for ammonium sulfate. And this is not any different than what we've been doing with stoichiometry. You're just going to add up the weight from the periodic table. And when I do that, I get a mass of 132.149 times 100 gives me a mass percent of 21.2% nitrogen in ammonium sulfate. Okay, and then the second one here, we're looking at the hydrogen. In this compound, we have 18 hydrogen. So I took 1.008 times 18, so I took the mass of hydrogen, which is 1.008 times 18, and that gave me a total of 18.144. Then I divided by the mass of this entire compound. And this entire compound, when I add it up, gives me a mass of 154.244. Multiply this by 100 because we want a percent, and that gives me 11.6% hydrogen in C10H18O. Okay, so that's how you find mass percent. Total mass of the element over the mass of the compound times 100. Okay, the second type of problem that I'm going to show you is finding what's called an empirical formula. Your empirical formula is your simplest formula possible. So for example, if I have a chemical formula that looks like this, the empirical formula would be this formula simplified, which would be C2H5. So that's what we're going to be finding here. We're going to be finding the empirical formula. It's our simplest formula. And when you're finding your empirical formula, you're given one of two things. You can be provided with grams of each element, or you can be provided with your mass percents. And you're going to solve it the same way, whether you're given grams or percents. The only difference is this. If you're given percent, you can just take these percents and turn them into grams. And that's because if I had 100 grams of this compound and 88.8% was copper, that would tell me that I have 88.8 grams of copper. And if I had 11.2% oxygen in my 100 grams, that would tell me that I have 11.2 grams of oxygen. So whenever you're finding an empirical formula, the first step is to take your grams, or if you're given percents, just turn it into grams. And then from there, you're going to go to moles. So if you're not at moles, go to moles. This still applies. When in doubt, go to moles. And this is grams of copper. So I need to cancel grams of copper, and I need to go to moles of copper. So I'm going to use the weight from the periodic table, and rounding less is better with these types of problems. So I'm going to do a minimum of 4 significant digits. So this gives me 1.3974 moles of copper. Okay, then I'm going to do the same thing with the oxygen. Oxygen has a mass of 16.00 or 16, and we want to go to moles. And the reason we want to go to moles is we want to compare them according to their proportion. And when we're looking at the proportion, we want to compare them in terms of moles. Because according to Avogadro, there are 6.02 times 10 to the 23rd particles per mole. So we want to compare them in terms of moles. And when I divide this, I get 0.7000 moles of oxygen. Okay, so take your grams. If it's percent, make it grams. Go to moles. Our next step is to pick the smaller of the two answers and divide them both by the smaller number. 0.7 is smaller than 1.39. So I'm going to divide both of these by the 0.7. And that's going to give me exactly 1. And when I divide this number, this gives me 1.996, which is close enough that I can just go ahead and round that to 2. So if it's less than 1/10 away from the nearest whole number, just go ahead and round it to that whole number. All right, so what I have here is I have 2 coppers and I have 1 oxygen. So what I just found are the subscripts that go into my formula. So it's Cu2O1. And whenever you're writing your formula, just remember that metals always go first. So in this case, copper comes first because it's the metal. So this is my empirical formula. Okay, I'm going to show you how to do another one. This one has 3 elements. And so I'm given percents. And because I'm given percents, I'm just going to turn that into grams. So we are permitted to magically turn those into grams. Just be really careful when you copy them down. A common mistake is to mix up which element is which. And then for each one, we're going to go to moles. So I want to get rid of grams of oxygen and go to moles of oxygen. And get rid of grams of chlorine and go to moles of chlorine. And get rid of grams of sodium and go to moles of sodium. Okay, for the grams per mole, I just use the weight on the periodic table. And for sodium, I use 22.99. For chlorine, I use 35.45. And for oxygen, I use 16.00 or 16. And when I solve, I want to make sure I don't round the number too much. So for the Na, it gives me point. Okay, so this gives me 0.8177. And this is going to be moles of sodium. And for the chlorine, it gave me 0.8181. And for the oxygen, it gave me 3.2625. Okay, the last step that everyone forgets is to pick the one that's the smallest. And in this case, that's the sodium. And divide them all by that number. So when I divide this, I get exactly 1. And then for the chlorine, I get 1.0004, so we can go ahead and round that to 1. And for the oxygen, I get 3.9898, which rounds to 4. Okay, and then when I write the formula, I have a metal here. And so the metal goes first, and there's 1 Na. You don't need the 1 here, but we have 1 Na. Notice we have more than 1 nonmetal left over. We have 4 oxygen and 1 chlorine. If you have more than 1 element left over with your metal, that means that we are looking at a polyatomic ion on your pink sheet. And so when I look on my pink sheet and I look for something that has 1 chlorine and 4 oxygen, I see in the first column I have ClO4. It's pretty close to the bottom, and that's perchlorate. So this is going to form sodium perchlorate. And that'll help you decide what order to put this in. So this is NaClO4, which happens to be -1, and this is +1. Okay, number 2. Go ahead and try that one. And when you solve for this one, you should get NaNH2 as your answer. So try this one. Make sure that you're able to get the NaNH2. Okay, so that's how you find your empirical formula. Okay, now you will also have problems where you have to find the chemical formula. Sometimes you will have to find the empirical formula and the chemical formula. When finding the chemical or molecular formula, you're still going to start by finding the empirical formula. So we're going to start the same way every time. The only difference with this problem is that we're given the weight, which we are going to ignore for now. We're only going to be paying attention to the percents for now. We're going to take our percents and we're going to find our empirical formula. So that's our step one. So I'm going to take the 62.07 grams of carbon. And I'm going to take my 10.34 grams of hydrogen. And I'm going to take my 27.59 grams of oxygen. So if you're not at moles, go to moles. This still applies. When I get my moles of carbon, I get 5.16819. And I'm not rounding very much here at all. Okay, for this one, for the hydrogen, I get 10.2579. We want to do a minimum of 4 digits. And then for the oxygen, I get 1.724375. Okay, so we're trying to get our subscripts. Clearly these are not subscripts right here. We still have one other step. We have to divide by the one that's the smallest, and that would be the oxygen. So divide them all by the moles of oxygen. And this is going to give me 3. It's going to give me a number very close to 3. It's going to give me a number very close to 6. And it's going to give me exactly 1. When you have a compound that contains carbon and hydrogen, and there is not a metal in it, we call that an organic compound. So if it contains carbon and hydrogen, it's organic. When you have an organic compound, we are going to put it in alphabetical order. So what that means is this: the carbon has to go first, and we have 3, followed by the hydrogen, we have 6, and then the remaining elements go in alphabetical order, and we just have oxygen, and there's 1. When we have organic compounds, you might see carbon and hydrogen with nitrogen and sulfur and phosphorus and oxygen. Just remember that the C is first, then the hydrogen, and the remaining elements in alphabetical order. So what I just found here is called my empirical formula. The percents give you the empirical formula. Okay, our next step is we want to see if my grams per mole matches up to what was provided for me. If the grams per mole of this compound is 116, then the chemical formula or molecular formula is the same as the empirical formula. So what I'm going to do is add this up and see what I get. So when I take C3H6O and I add it up off the periodic table, 12.01 times 3 plus 1.008 times 6 plus 16 gives me a mass of 15.078. grams per mole. That does not match up to the 116. So my next step is to take the given grams per mole, which is the 116, so you take the molecular weight that's given and you divide by the molecular weight of your empirical formula. And when you do this, you definitely should get something close to a whole number. If you don't get something close to a whole number at this point, then you need to go back and check because you did something wrong. So when I divide this, I get something very close to 2. And what that means is that I need to double my numbers in my empirical formula. So instead of C3, I need to double that, so it's C6. Instead of H6, I have to double that, so it's H12. And then instead of O1, I have to double that, so it's O2. And if you were to take, this is your chemical or molecular formula, and if you were to take your grams per mole and add it up for this compound, you should get the number that I gave you, the 116. And that's how you can always check your final answer. Okay, so if the empirical formula matches what I give you, then the empirical formula and the chemical formula are the same. If it doesn't match, then they're different, and you need to take the weight that I give you in the problem divided by the weight of your empirical formula, and that will give you a factor to multiply by your original subscripts. Okay, let's try one more. This one's a little bit more complicated. Okay, so this one we're looking at ibuprofen, and we have 75.69 grams of carbon. We're just going to make these grams. We have 8.80 grams of hydrogen, and we have 15.51 grams of oxygen. And then I'm going to go to moles. So I have 12.01 grams per mole of carbon, and I have 1.008 grams per mole of hydrogen. Notice even though hydrogen is diatomic and so is oxygen, they're only diatomic when they're alone. This hydrogen is not alone. That's with carbon and oxygen. The oxygen is not alone. It's with hydrogen and carbon. So you're only going to do one of each element in this case. Okay, so for my carbon here, I get 6.3075 moles of carbon. And for the hydrogen, I get 8.730159 moles of hydrogen. And for the oxygen, I get 0.969375 moles of oxygen. And then the step we don't want to forget is to pick the one that's the smallest and divide by that smallest number of moles. And oxygen has the smallest number of moles. Okay, so when I divide this for my carbon, I end up with 6.507. And for the hydrogen, I get 9.005. Notice I'm doing a minimum of 4 significant digits. And then this one, I'm going to get exactly 1. All right, so this is an example of where we don't have something that is near a whole number. It's not less than 1/10 away from the nearest whole number. This right here is smack dab between two numbers. If it is not near a whole number, then you need to multiply it by a factor to make it near a whole number. And I can make this near a whole number if I double it. And by doubling this, that makes it very, very close to 13. But if I double the carbon, I also have to double the hydrogen, making this 18. And then I also have to double the oxygen, making this 2. Okay, so sometimes you have to double it. Sometimes you have to triple it to make it near a whole number. There are also some circumstances where you have to quadruple it to make it near a whole number. But generally you're going to see, if you see something like this, generally you're just going to have to double them. And so what I have here, because this is organic, it has carbon and hydrogen and oxygen. My empirical formula that I get from the percent is C13, carbon goes first, then hydrogen, and then the oxygen, and we have 2 of those. Okay, now we're going to see if this matches up with the weight that was provided. And we're told that the weight provided, that it should match up to, so the chemical compound should have a weight of 206. So I'm going to add this up. I'm going to take 12.01 times 13 off the periodic table, plus 1.008 off the periodic table times 18, plus 16 off the periodic table times 2. And when I add that up, I get a total weight of 206.274 grams per mole. Okay, so my given grams per mole provided to you in this question was 206. And my empirical formula, grams per mole, is this 206.274. So when I divide this, I definitely get something close to a whole number. I get 1, something very close to 1. And so what that tells me is that this is the empirical formula, and it is also the chemical, also called molecular formula. Okay, so that's how you find your empirical formula, chemical formula, and your mass percent.